Picture this. You're piloting a plane weighing dozens of tons. But you're not landing on concrete. You're not landing on asphalt. You're landing on a sheet of ice floating in the Arctic Ocean. No runway. No margin for error. And if the ice cracks, you don't crash. You sink. This isn't science fiction. This actually happened. Engineers actually convinced pilots to do this. And for a brief moment in history, it worked. Today, you're going to find out why anyone thought this was a good idea in the first place, and what went catastrophically, predictably wrong. But here's the twist. This failure taught us more about engineering limits than most successful projects ever could. So buckle up. We're going to the coldest, most unforgiving place on Earth, where the only thing crazier than the conditions was the solution. Let me set the scene for you. The Arctic. Not the, oh, it's chilly, kind of cold. The your eyelashes freeze together kind of cold. We're talking minus 40 degrees Fahrenheit. Sometimes colder. The kind of cold where exposed skin gets frostbite in minutes. Now imagine the landscape. Endless white. No trees. No buildings. No landmarks. Just ice, snow, and a horizon that stretches forever in every direction. During winter, the sun doesn't rise for months. You're working in perpetual twilight, with stars overhead even at noon. It's beautiful in a terrifying way, like staring into the void and realizing the void is staring back. Here's the thing about the Arctic. It's not just remote. It's aggressively remote. There are no roads leading there because, well, there's nothing to build roads on. The ice shifts. The ground, when they're ice ground, is permafrost that turns to mud in summer. You can't just call AAA if your vehicle breaks down. You can't order supplies from Amazon Prime. If something goes wrong, you're on your own for days, maybe weeks. And yet, people needed to be there. See, during the mid-20th century, the Arctic wasn't just some frozen wasteland scientists occasionally visited. It was becoming strategically critical. This was the Cold War era, and the Arctic was essentially the shortest route between two superpowers staring each other down. Planes needed to fly surveillance missions. Troops needed supplies. Scientists needed equipment. And all of that required one thing that didn't exist: an airport. Just build one, you might say. How hard could it be? Well, let me tell you about trying to build a conventional airport in the Arctic, and you'll understand why engineers started considering other options. First, there's permafrost. That's permanently frozen ground, right? Except it's not really permanent. When you try to build on it, your construction equipment generates heat. The permafrost thaws. Your foundation turns into a muddy soup. Your runway buckles and cracks. Second, there's the weather. Storms can last for weeks. Visibility drops to zero. Equipment freezes solid. Workers can barely function in the cold, even with the best gear. Third, there's logistics. Every single thing, every bag of cement, every steel beam, every gallon of fuel has to be shipped in at enormous cost. We're talking millions of dollars just to get your materials on site. And fourth, the ice itself. Even if you find solid ground to build on, the sea ice around you is constantly moving, grinding, creating pressure ridges that could destroy anything in their path. So yeah, building a normal airport? Not really feasible. But without airports, the Arctic remained a blind spot. A massive strategic vulnerability. An entire region of the planet where you simply couldn't project power or respond to emergencies. And that's when someone, and history isn't entirely clear on who said it first, uttered a sentence that would change everything. What if we just land on the ice? Imagine being in that meeting. You're a military officer or a government official. You just heard all the reasons why building a conventional airport is basically impossible. The budget is astronomical. The timeline is years. The technical challenges are nearly insurmountable. And then some engineer, probably sleep-deprived, definitely caffeinated, raises their hand and says, "Okay, hear me out. The ice is already there. It's flat. It's strong. What if we just use it?" The room goes silent. Someone coughs awkwardly. Another person wonders if this is a joke. But the engineer keeps going. "No, seriously. Think about it. The ice can be several meters thick. That's strong enough to support weight. It's already level. Nature basically did half the work for us. And here's the thing. The logic wasn't completely crazy. Arctic sea ice, when it's thick enough, is incredibly strong. Indigenous peoples have been traveling across it for thousands of years. Icebreaker ships dealt with it constantly. There were records of heavy equipment being transported over frozen lakes. So the concept wasn't pulled out of thin air. There was precedent. But, and this is a big but, there's a massive difference between driving a sled across ice and landing a multi-ton aircraft on it at high speed. When you land a plane, you're generating enormous forces. The impact, the friction, the vibration, and you're doing it repeatedly in the same spot, which creates stress points. Plus, ice isn't like concrete. Concrete is predictable. Engineers understand concrete. They have formulas, equations, safety factors calculated to absurd decimal places. Ice is alive. It moves. It expands and contracts with temperature changes. It develops cracks overnight. It has weak spots you can't see from the surface. As one engineer reportedly said during the planning phase, everything we know about building runways just got thrown out the window. We're making this up as we go. Which is exactly what you want to hear when you're about to risk pilots' lives, right? But here's the reality. They didn't have better options. The need was urgent. The conventional approach was too slow and too expensive. So they decided to try it. The project that emerged had a simple name, Ice Runway Operations. But there was nothing simple about what they were attempting. The concept was straightforward enough. Find a large, thick ice sheet. Survey it thoroughly. Clear and level the surface. Mark out a runway. Test it extensively. Then, and only if everything checked out, bring in a plane. Easy, right? Narrator's note, it was not easy. Let's talk about the actual process, because this is where the story gets really interesting. Step 1. Find your ice. You can't just land anywhere. You need ice that's thick enough, stable enough, and large enough to accommodate an aircraft. Generally, they were looking for ice at least 6 to 8 feet thick, sometimes more, depending on the aircraft weight. How do you measure ice thickness? Well, in the early days, it involved a lot of drilling. Teams would go out onto the ice with specialized drills and take core samples every few meters. It was tedious, cold work. One engineer described it as like checking the foundation of a building, except the building is trying to kill you. They also used ground-penetrating radar in later operations, but even that had limitations. Ice isn't uniform. You might have 8 feet of solid ice in one spot and a weak point 20 feet away. Miss that weak point in your survey, and you could have a catastrophic failure during landing. Step 2. Prepare the surface. Natural ice is not smooth. It's covered with snow drifts, pressure ridges, and rough patches. Before any aircraft could land, crews had to clear and level the runway area. They used everything from shovels to heavy machinery, basically snow plows on steroids. The goal was to create a relatively smooth landing strip, typically about 10,000 feet long and 200 feet wide. That's roughly 2 miles of ice that needed to be perfect. And remember, we're doing this in minus 40-degree weather, where your equipment keeps breaking down and your workers need breaks every 20 minutes to avoid frostbite. It's like mowing a lawn, except the lawn is the size of a small airport and trying to give you hypothermia. Step 3. Mark the runway. This sounds simple, but it's crucial. In whiteout conditions, which were common, pilots needed clear visual references. They used flags, lights, and painted markers to delineate the runway edges and centerline. The challenge? The ice was constantly moving. Slowly, yes, but moving. Markers placed one day might be several inches out of position the next. Teams had to constantly resurvey and adjust. Step 4. Testing. Before any aircraft landed, they ran extensive tests. They drove heavy vehicles across the runway to check for weak spots. They measured how the ice responded to weight distribution. They monitored for cracks. And here's something fascinating. They learned to listen to the ice. Experienced crew members could literally hear when ice was under stress. It makes sounds, pops, groans, creaks as it adjusts to pressure. If you heard the wrong sound, you stopped what you were doing and reassessed. One veteran of these operations said, "The ice talks to you. The trick is learning its language before it screams." Step 5. the actual landing. This was the moment of truth. A pilot approaches an ice runway for the first time. Everything in their training tells them this is wrong. Runways are supposed to be solid, permanent, reliable. This runway was none of those things. The approach was carefully calculated. Slower speeds, gentler touchdown, constant monitoring for any signs of structural failure. The pilot had to be ready to abort and go around if anything seemed off. And the first few times, absolutely terrifying for everyone involved. But then it worked. The plane touched down. The ice held. The aircraft rolled to a stop without breaking through. They had done it. They had successfully landed an aircraft on ice. And for a brief, shining moment, it seemed like they had solved the impossible problem. Once they proved the concept, ice runways became almost routine, at least as routine as landing on frozen ocean can be. Multiple locations across the Arctic established ice runways. They developed standard operating procedures. They trained crews specifically for ice operations. What started as a desperate experiment became, for a time, a legitimate operational capability. Aircraft began flying regular missions to Arctic locations that had been previously inaccessible. Supplies flowed. Personnel rotated. Scientific research expanded dramatically. The flights brought in equipment for weather stations, supplies for research bases, fuel for generators, food for personnel. Without these ice runways, many Arctic operations would have been impossible. And here's what's really cool. They got good at it. Engineers learned to predict ice behavior. They developed better surveying techniques. They understood how different temperatures affected ice strength. They created detailed manuals and guidelines. Pilots learned the unique challenges of ice landings, the way the surface could be slippery, how to judge braking distance, when to abort if conditions weren't perfect. It became a specialized skill set, a niche expertise. There were people who became legendary in Arctic aviation circles for their ice runway operations. You could see it in the reports from that era. There's this sense of accomplishment, of human ingenuity triumphing over nature. Phrases like routine operations and established procedures start appearing in documents. They held training exercises. They ran supply missions. They even hosted VIP visits where officials would fly in to see this marvel of engineering improvisation. One report from the period proudly stated, "Ice runway operations have proven safe, reliable, and cost-effective." And that's usually when nature reminds you who's really in charge. Here's the thing about ice. It's not your friend. It's not your enemy either. It's completely indifferent to your plans, your schedules, and your carefully calculated safety margins. The problem started small, cracks appearing where they shouldn't, sections of runway settling unevenly overnight, strange sounds from the ice that veterans couldn't interpret. At first, these were treated as anomalies. You survey more carefully. You adjust your procedures. You add safety margins. But the incidents kept happening. There's a concept in engineering called failure modes. It's all the different ways something can go wrong. With conventional runways, failure modes are well understood. Concrete can crack. Asphalt can buckle. But these failures are gradual and predictable. Ice failure modes are different. Ice can fail catastrophically and without warning. A runway that tested perfectly safe in the morning could develop a fatal flaw by afternoon. Temperature changes could create internal stresses that weren't visible from the surface. The ice wasn't static. It was part of a dynamic system. Ocean currents, tides, wind, temperature gradients. All of these factors interacted in complex ways that weren't fully understood. One incident report describes a runway that had been in use for weeks. All inspections showed it was solid. Then, overnight, a crack opened right down the center line. Not a small crack, we're talking several inches wide and running for hundreds of feet. Why? Best guess, a current under the ice had changed, creating temperature differentials that caused the ice to split. There had been no warning, no way to predict it. The runway that was safe at sunset was unusable by sunrise. Another report describes ice drumming. When you land on it, the ice vibrates like a drumhead. This happened when the ice was floating on water with just the right depth and temperature. The vibration itself wasn't immediately dangerous, but it was unnerving and indicated the ice was more flexible than calculations predicted. Then there were the pressure ridges. As ice sheets drift and collide, they buckle upward, creating ridges that could be dozens of feet high. These ridges could appear near a runway, or even within a runway, sometimes in a matter of hours. Imagine prepping for a landing, checking that your runway is clear, and then finding a 3-foot-high ice wall has appeared in the middle of it because 2 ice sheets decided to say hello. The question pilots started asking wasn't if something would go wrong, but when, and the psychological toll was real. Every landing became an exercise in controlled fear. You trusted the surveys. You trusted the engineers. But you also knew that the ice didn't care about surveys or engineering calculations. One pilot was quoted, "Landing on ice never becomes normal. Every single time, some part of your brain is screaming, this is a terrible idea." The breaking point came when they realized something fundamental. The runways were getting less reliable over time, not more. As ice was used repeatedly, it developed structural fatigue. The constant impacts, the weight stress, the temperature cycling, all of it took a toll. Microscopic cracks would form and propagate. What started as a perfectly solid ice sheet would gradually weaken. And here's the terrifying part. This weakening wasn't always visible or measurable with their available technology. An ice runway could look perfect and test safe right up until the moment it failed. The most hair-raising moment? There are reports of an aircraft landing successfully, completing its mission, and then being unable to take off because the runway had deteriorated during the few hours it was on the ground. The crew was essentially stranded on ice that was slowly becoming unsafe beneath them, racing against time to either repair the runway or somehow get their aircraft off the ground before the ice gave way completely. That incident ended safely, barely, but it drove home a crucial point. You can't control ice. You can only respect it. And sometimes, respect means knowing when to stop. So what do you do when your brilliant solution starts showing fundamental flaws? For ice runway operations, the answer came gradually through a combination of near misses, detailed analysis, and honest recognition of limitations. The military and aviation authorities started asking hard questions. How many close calls were acceptable? What level of risk was justified? Were they pushing luck too far? This is where the story gets interesting from an engineering ethics perspective. Because the ice runways technically worked, most of the time, aircraft landed and took off successfully. Supplies were delivered. Missions were completed. But most of the time isn't good enough in aviation. The standard isn't usually safe. It's safe enough that failure is extraordinarily unlikely. And ice runways couldn't meet that standard consistently. The investigations revealed some uncomfortable truths. First, they had been lucky. Several incidents could have ended in disaster, but didn't, essentially by chance. A crack appeared after the plane passed, not before. A weak spot was in a section the plane didn't taxi over. The ice held for just long enough. Second, their understanding of ice mechanics was incomplete. They had learned a lot through experience, but there were still phenomena they couldn't predict or explain. They were essentially operating on educated guesswork. Third, the risk was increasing over time. As operations expanded and more flights used these runways, the probability of a catastrophic failure grew. It wasn't if something terrible would happen, but when. The decision to scale back ice runway operations wasn't made all at once. It was gradual, driven by accumulating evidence and changing risk assessment. Some locations continued operating ice runways for specific purposes. Others developed alternative solutions. Floating platforms, expanded range for aircraft, better supply chain logistics that reduced the need for Arctic bases. But the era of treating ice runways as a standard operational capability was over. Here's what's crucial to understand. This wasn't a failure. Not really. The project accomplished what it set out to do. It proved that landing aircraft on ice was possible. It provided critical capability when no other options existed. It pushed the boundaries of what engineering could achieve in extreme environments. But it also taught a more important lesson. Just because you can do something doesn't mean you should keep doing it. Sometimes the bravest decision isn't to push forward despite the risks. It's to acknowledge the limits and step back. So what happened to ice runways? Did they disappear completely? Not quite. Today, ice runways still exist, but they're used very differently. They're typically seasonal operations on frozen lakes or very thick sea ice, with extensive safety protocols. They support Antarctic research stations, remote mining operations, and specialized military exercises. But they're no longer seen as a permanent solution to Arctic aviation challenges. They're a tool, useful in specific circumstances, but with well-understood limitations. The story of ice runways connects to a larger theme in engineering and human ambition: the relationship between possibility and sustainability. We're really good at proving things are possible. Put enough resources, intelligence, and determination into a problem, and humans can accomplish astonishing things. Landing planes on ice? Sure. Building bases in Antarctica? Done. Creating habitats in space? Working on it. But possibility is just the first step. The harder questions are about sustainability, safety, and long-term viability. Ice runways proved that Arctic aviation was possible, but they also proved it wasn't sustainably safe using that particular method. Today, Arctic aviation relies on different solutions. Some locations have managed to build conventional runways on carefully prepared foundations. Others use floating platforms anchored in ice. Still others have extended aircraft range, so they don't need forward bases. These solutions are more expensive and more complex than just landing on ice, but they're also more reliable and safer. The knowledge gained from ice runway operations wasn't wasted, though. It contributed to understanding of ice mechanics, cold weather operations, and extreme environment engineering. Scientists studying glaciers and ice sheets use some of the same surveying techniques developed for these runways. There's something almost poetic about the ice runway story. It's about humans trying to impose order on chaos, seeking stability on a surface that's fundamentally unstable, trying to make permanent what is inherently temporary. The ice doesn't care about your engineering calculations. It doesn't care about your mission timelines. It exists according to its own rules, shaped by forces far more powerful than any human endeavor. And maybe that's okay. Maybe part of wisdom is recognizing that some problems don't have permanent solutions. Some challenges require constant adaptation rather than fixed infrastructure. The engineers who worked on ice runways weren't foolish. They were brave, creative, and working with the resources they had. They pushed boundaries that needed to be pushed, but they also learned when to stop pushing. And that might be the most important lesson of all. So here's what we've learned. Ice runways were a triumph of engineering improvisation in impossible conditions. They worked just well enough to prove the concept, and just poorly enough to prove it shouldn't become standard practice. The airports built on ice shouldn't have existed, and ultimately, they mostly don't anymore. But for a brief moment in history, they did exist. Pilots landed planes on frozen ocean. Cargo was delivered to places that seemed unreachable. Human determination, for better or worse, found a way. Sometimes the most insane projects don't need to succeed permanently. They just need to show us where the limits are. And the Arctic ice? It showed us exactly where ours were. Thanks for watching. If you enjoyed this deep dive into engineering at the edge of possibility, hit that subscribe button. Next time, we're exploring another place humans probably shouldn't have tried to build things, but did anyway. Because if there's one thing we've learned from history, it's that impossible is just an invitation to someone, somewhere, to prove otherwise. Even if the ice disagrees,